So I'm Mark Eijsermans. I'm the other person on the team that's been working on all this stuff. I'm going to talk about service meshes and kind of some of our experiences with it, what they are, what the benefits are, and maybe you would be interested in considering it for your own cluster, and like that might be appropriate for you. So let's start off by considering like a really simple example. There's one service talking to another service. So service A is making a call to service B. A request over the network. It's a simple kind of call, makes a request, gets a response back. But in reality, you actually have more than one instance of a service running. You might have 3, you might have 10, you might have 100. So the first problem is, where are these services running? And after deployments, where are they going to live once everything changes? So there's churn in the cluster. The first thing to consider is, well, where is the service that I want to talk to? And so where would you put that logic? Normally, you would put that inside of the application. How would I find a service? Look in service discovery or DNS or something. And then another problem, what if you make a call to that service and it fails? Should you retry? And how often do you do that? Do you keep retrying, and what's the logic there? So again, you could put that logic in your application. So the solution to that, or one solution, is a fat client model, which is putting all that logic inside of the application itself. So how to find the service, retries, and everything to do with calling out to a service over the network. And so with that, it's pretty simple. It's easy to understand. I guess you can customize it if you want, like if you want to treat one service different than another. But there's also a lot of cons to that, which is service discovery is actually pretty tricky to get right. There might be different consistency models with your service discovery. Maybe you would crowd or overload your service discovery. Should you trust the entries in service discovery? Is that actually like the truth? Retry logic is also really tricky. And it's hard to get right. So how many times do you retry? Should you back off on retries? Should you add jitter, like adding randomness to it? So if you have a problem in your network or with a service, that you don't actually make the problem even worse by constantly hammering it over each other. So with that, then also, did every service in your cluster get it right? Did every service code this properly? And then what about if you're a polyglot service or a polyglot shop and you run Python and PHP and Scala and Golang? Did each of those languages do it right and all those frameworks get it right? So it's actually pretty tricky. I mean, initially you would think, well, hey, I'll just look up my service in DNS and I'll just do a retry and a for loop. But actually, it gets really kind of complicated. So another solution is the fat middleware approach, which is putting that logic of, say, service discovery and retries and more advanced logic into the network, the middleware, the networking middleware. And that's what a service mesh is, and we'll get into that. And that keeps your clients dumb. So it keeps your clients very simple. They don't need to encode a lot of the logic inside of them. And then any benefit that you put into this middleware, all languages will get the benefit of it. So here's a simple kind of service mesh. And this is something we built internally. It's our kind of first generation of a service mesh. This is before Kubernetes. This is before kind of all this. It's very simple to Airbnb Smart Stack, if any of you have heard of that. So what we have here is service A talks to service B, but instead of calling it directly, the request gets routed through Nginx. And Nginx is getting its like network topology and where services lives from console. Some people use HA proxy, talking to Zookeeper, but it's kind of the same idea, is that you've got a service discovery, and then you have a proxy that is actually handling the traffic and handling the requests. So with our initial kind of version 1 or generation 1 service discovery, is we got retries on 502s, which is nice. And it was really simple and robust, and when you put it in place, developers loved it. It was great, because it's very simple. When you make a request, you curl to localhost to some standard port /service/B. Now it's very simple. But we're talking about Kubernetes here, right? And we already have service discovery. So we use DNS. We make a request by calling b.default.service.cluster.local. It works nice. And we all know the power of a service mesh because Kubernetes actually has a really bare bones service mesh, if you think about it. Now, the way that it works is it's using kube proxy to set IP tables rules on each node, and it's communicating with the kube API. So the kube API is your service discovery, and your routing, your proxy, is IP tables. So it is a very simple service mesh, and we already know like how awesome that is. It makes things really great, but you don't get any of the kind of the advanced benefits. It uses random load balancing with IP tables, so that's kind of all you get. No retries, nothing more than that. Okay, so where do we go from here? So recently, in about the last year, there's been kind of a development of second generation, I guess, as I would call, service meshes. And so these are proxies that are designed for microservices. A lot of kind of intercommunication between services, high amount of churn, and some of these things might be running in a cluster. So Linkerd is Scala-based. It actually is probably the most kind of further along in development. It's reached 1.0. Envoy by Lyft is pretty great. You need to manually configure it for Kubernetes. And then Istio is probably, as Kubernetes user, is probably kind of like the one that is probably most appealing to us. As it is, it takes Envoy, and then it's actually hooking that in and orchestrating it with Kubernetes. And so that's kind of still in alpha/beta. So again, if we look at what this second gen service mesh looks like, it's the exact same thing. So as opposed to like the IP tables and kube API, it's actually just that userland proxy that's there, and it has its own kind of layer to deal with service discovery and on top of it. So it's a very similar kind of model. But what you get with it is a lot of benefits on top of that, not just service discovery, not just retries, but you get advanced routing, so again, retries. You get retry budgets, request deadlines, circuit breaking, if you're familiar with like Hystrix and some of the circuit breaking libraries. Latency observed load balancing, so which machine is responding or which pod is responding faster than another. Advanced orchestration, so you can do Canary and blue-green with Kubernetes, but it's a little bit trickier. And then some more advanced routing like per request routing. It standardizes your metrics and logging. You get a centralized control plane. It adds distributed tracing and makes distributed tracing a lot easier to integrate into your applications. Some of them have rate limiting. And then there's authentication, which is also a really important part, so we can add some security onto the network layer. So I'll talk about a few of these things, and not all of these service meshes do all of the things. Some do only a subset of these features, but a lot of them have overlap. So if you look into service meshes, these are some of the things that you might kind of consider yourselves. So retries. As I said before, what we did with our generation 1 service mesh is we got automatic retries on 5L2. So that's a bad gateway. That's an obvious one to retry. But you might want to get retries on idempotent reads. So like you got a get, and it's any 500 requests, you get a retry on that. And that'll kind of retry a lot more of the requests automatically for you. Back off. Again, we'd want to put kind of more intelligence into the retries and consistently deal with retries in the cluster. So we want to put jitter. We might want to have exponential kind of retries. And then if anyone here is using gRPC or planning to use gRPC, so a big part of that is having deadlines, so that throughout the request chain, there's an overall kind of timeout for the whole request chain. Some of the service meshes understand kind of gRPC deadlines and can deal with that, which is a neat little feature. So observed latency, you get a lot of benefit by actually load balancing based on the latencies that you're observing, not just round robining. So there's a lot more kind of intelligence there. You could have a pod that is sitting on the other side of the data center, or a pod that's in another zone, or you could have a pod that's on the same machine. And this pod on the same machine might be a lot faster. You'd assume that it'd be a lot faster. So there is a little bit of overhead with running a proxy as opposed to IP tables. And some of that is compensated by running, by doing the retries, and also by the observed latency, that you get a much more kind of consistent response rate. All right, and you get advanced orchestration. So as I was saying before, Kubernetes can do blue-green deployments. They can do canary deployments, but you're going to have to manually set service manifests, manually kind of update your manifest in Kubernetes, and that can be a little sort of slow going. What you get is some features of being able to have a centralized control plane to kind of switch and determine your routing. And I was saying before, per request canarying, which is an extremely interesting feature. So you set a header in your request saying, okay, I want to override down the chain of your requests. I want to override which service it goes to. I want it to go to one little canary that I've deployed for myself. I want to test out a feature. And if you set a header, it can then basically change your routing table dynamically on the fly, which is pretty powerful. If you want to actually canary something very specific and don't have to, some of you may dark launch and you set like a certain percentage of requests to a request, and that might be dangerous. Being able to do per request routing changes allows you to do extremely dangerous kind of things, but you're only doing it once or twice or to yourself, or it allows a lot greater flexibility. And then observability, as I mentioned before. So metrics and logs are standardized, they're amortized, and it makes the network a lot easier to understand. You can reason about it, and that's extremely hard to figure out. I mean, when there's a problem in a network, just trying to figure out what the hell is going on is probably the trickiest thing. Distributed tracing is something that probably a bunch of you have considered or maybe have implemented yourself. Retrofitting that into a service is a bit of work. Like you have to manually add distributed tracing libraries into your code. Some languages might not have the proper libraries. It's a bit finicky. Now, if you let the service mesh take care of the distributed tracing, all your application needs to do is just pass along headers. So there's kind of metadata headers, and your application simply needs to shepherd it along. And the router itself, or the proxy, will do all of the creation of spans and subspans, and you got to see like all the creation of these different sort of request chains along the way. It'll handle that for you, and then take care of shepherding it onto a collector. So there's a bit less stuff that you would then need to put into your application itself. So authentication, and this has been a big thing for us. Security was having problems with us. Initially, when we kind of moved stuff into a scheduler using containers, we first kind of started running on Mesos. And with that, and same with Kubernetes, when you run it as a container in a scheduler, you lose your security, your traditional firewalling. And that was a big problem. So you couldn't say, well, this security group in Amazon can talk to that security group. You lose all that. Everything is wide open. And it's a hard thing to swallow, and I think it's a hard thing to swallow for probably a lot of you guys as well. So there's an opportunity, and I think actually a huge opportunity to put a lot of that security back into the network. So you can wrap a request transparently from the perspective of the application, be able to sort of secure the communication over the wire. So sometimes you also have third-party services that you're running in there. I think back in the day, Memcache didn't have any authentication. There was nothing. I'm sure there's a bunch of stuff that we're running that doesn't actually have auth in there. I don't know what stories with Memcache now, but so Istio is probably the most advanced in this. So the way that it works is, your service talks to the local proxy. It transparently wraps it with TLS. And then using service alternative names on the receiving end, this guy over here is then going to validate it. Hey, I've got a request coming from service A. And is this guy allowed to talk to me? Is this okay? So you get encryption over the wire, and then also validation of who's allowed to talk to each other. So there's a couple things that I'd like to mention of stuff that we've learned kind of along our journey. So there's different ways of deploying a proxy in a service mesh. So there's Sidecar, which is putting each pod, so this guy here is a pod, each pod has its own proxy, and the other way is shared host. So initially what we did with our generation 1 service mesh is we did the shared host. But actually, kind of where we've moved towards is like a per pod sidecar model. And so the benefits of a sidecar model are that you get the resource utilization of the proxy is tied to the limitations of the pod. It's contained to the pod's own sort of CPU and memory constraints. Also failure, if you have failure in the proxy, it's going to be limited to the pod or the service. And then it also makes end-to-end encryption impossible. So what I was talking about with authentication, you kind of only can run it if you're running it on a per pod sidecar. So if you're doing on a host level, what happens is then that host proxy has to be kind of aware of all of the certificates running around and all of the different services in your cluster, which is basically defeating the point. So, but there are some benefits of running per host. Since you have one machine, it's better at connection reuse. It's better at resource utilization. You're only running one of them, so there's only one kind of process that's taking over. And if you are running proxy, how do you redirect the traffic of your pod, of your service? How do you redirect it into that proxy? And so there's a couple of techniques. So you could use the HTTP proxy environment variable, and a lot of languages and frameworks actually respect this. So you could say, well, I'm going to do that, but it only works for HTTP. And I mean, most of us are probably writing services that are RESTful, so that might work for you. You can manually override the host header when you're sending out a request. You could do some Etsy host hacks, which is probably a really bad idea. And IP tables per pod. So this is kind of the recommended approach now, is that in the pod, you set IP tables that says any ingress and egress traffic, reroute it to that proxy, and let the proxy kind of handle it. So the nice thing with that is that it works with layer 3 all the way to layer 7, so you can run any kind of protocol through there. That's how Istio works, and that's kind of the sort of the current kind of sort of best technique for kind of redirecting your traffic. Another thing is that your clients still must behave. So you have to trap, a shutdown. You have to drain your connections cleanly. You have to do all that stuff. You just have to be like a good service. And as I was saying before, with per request routing and distributed tracing, is that you're going to have to forward headers. So if you have Zipkin headers or there's some special headers that the service mesh is using, all your application really needs to do is just there's a subset of headers you need, and if something comes in and you're making a request to another service, just forward those on. It's actually pretty simple. And then retries. If you're going to put the intelligence in the network, you want the service itself to remain dumb. So you want to have a second layer of retries on top of it. So you just have to be aware of that, and your developers have to be aware of it too. And then with circuit breaking, it's the same thing as retries. If you're using Hystrix, your circuit breaking needs to be a lot more aggressive than the networking, than the circuit breaking in the networking. So it's just something that you have to be aware of. Developers need to be a little bit aware of how the network acts. So that's kind of what we found when we've been implementing it ourselves. So yeah, that's service meshes.